For our last video in chapter 21, we're going to talk about the fun stuff, fission and fusion. Those are both parts of what are called transmutation reactions, okay? Nuclear transmutation, conversion of one nuclide into another. Now, the things we covered in video 2 were transmutation reactions as well, right? Because radioactive decay, right? Changed the parent nuclide into the daughter nuclide, okay? Got more stable. Okay. But transmutation reactions can also occur by the reaction of a nucleus with another particle, okay, putting it together with something else instead of it just decaying. That can happen through the use of things like particle accelerators. These things are superconducting electromagnets, right? Thinking about another application of superconductors from chapter 19. They use both magnetic and electric fields to speed nuclear particles around in a vacuum, okay, to reach extreme kinetic energies that are necessary for a transmutation reaction to occur. And the most famous one, right, is at CERN, which is outside of Geneva, Switzerland, right, the Large Hadron Collider, okay, which is at CERN, the European Organization for Nuclear Research. Here you see a glimpse inside the tunnel. Here's a bird's eye view of where that tunnel is underground, okay, and it's crazy large. Okay, in circumference, just shy of 17 miles, okay, to get those speeds necessary. So what are these things used for? What types of reactions do we see there? Well, those particle accelerators, those particle accelerators, like the LHC, have been used to synthesize and isolate a bunch of artificial elements, everything at the back end of the periodic table. Okay, and here we see an example of neutron bombardment. Take uranium-238, speed up a neutron, collide them together. You make uranium-239, okay, which undergoes electron emission to form neptunium-239. Okay, that goes under further electron emission to form plutonium-239. And those are a lot of examples of the kind of reactions we see from these things. Everything with an atomic number above 92, most of them have been synthesized this way, and those are called transuranium elements. Here's a bunch of other examples of transuranium elements, and this is where we get a lot of those fun names on the periodic table, right? Americium for America, Californium, get even more specific for California, Mendelevium for Mendeleev, right? We discovered the periodic table, and others. But we have to be careful with these larger, heavier nuclei because they have lower binding energy per nucleon, which is something that we talked about in the first video. And that means that they're prone to falling apart via nuclear fission. Okay. Nuclear fission is the process of a large nucleus breaking apart into smaller pieces. And usually we see this be initiated by neutron bombardment. Okay. And the reason for this is these heavier elements, smaller binding energy, right? Less stuff holding it all together. So then we add in another neutron, it breaks apart, right? It exceeds the energy there. So it decomposes into more stable elements that have higher binding energies per nucleon and are therefore more stable. What's that look like as a picture, this process of fission? Well, I take my uranium-235 here, hit it with a neutron, and it turns into uranium-236. But in doing that, I've changed the neutron to proton ratio and I've changed the binding energy per nucleon. Right? So all of a sudden, with just one extra neutron, it's like, whoa, hold on, buddy, that's too much. So it breaks down into smaller, more stable nuclides. Okay? But it also releases a lot of energy. Okay? A lot of energy, and it releases additional neutrons as well. And there's a lot of possible products that we can get from this. Look, here's a bunch of other examples, okay? And we typically see two products, right? It splits into two things. We form a lighter one and then one that's about 50% heavier. Okay, general theme, not hard and fast rule. But the key thing to look at is the energy and the neutrons that are given off there, right? Huge amounts of energy. If I'm comparing energy sources, right? Nuclear, some people tend to be afraid of. but a kilogram of uranium-235, if used in a nuclear reactor, gives you 2.5 million times a kilogram of coal, right? So pound for pound, 2.5 million times the amount of energy. It's crazy, right? So we get energy, and we also get neutrons that are produced from a fission reaction. And keep in mind, it was a neutron bombardment that started it off in the first place, right? So those neutrons that are produced can cause fission further along, and that's called a nuclear chain reaction. If we can sustain that reaction, that nuclear material is said to be fissile or fissionable. And this is what it looks like. All right, well, the quality of this slide is terrible. I apologize, but you get the theme here, right? Neutron bombardment starts it off. We produce 3 neutrons, and each one of those neutrons can start another fission reaction, and we keep getting energy. Okay. So we can sustain that, right? Nuclear fission becomes self-sustaining when the number of neutrons produced is either equal to or chances are greater than the number of neutrons that are absorbed. And in order for something to become self-sustaining, it depends on a lot of factors. It depends on what material we're working with specifically, right? How pure it is. You've heard about purification for nuclear reactors, the temperature we're working at, even the shape, right? The surface area, and how the reaction is controlled, which we'll touch on in just a second. A couple other key terms. The amount of material that we need to support a self-sustaining chain reaction, that's called the critical mass. If you don't have enough from that, it's called subcritical, right? It won't continue on, even if you have enough neutrons, because you do need a certain amount of material. But if you have too much, right, you've exceeded the critical mass, and it causes the rate of fission to speed up, that's a term you've probably heard, the supercritical mass, right? Which, depending on your application, you probably want to avoid, right? And here's what those look like, right? Subcritical mass, I don't get enough neutrons for the reaction to continue. Critical mass, I get enough neutrons to continue popping off energy. So where is the application where you do want the supercritical mass? Well, I'm thinking about wartime and atomic bombs. How's an atomic bomb made? 101. Hopefully this video doesn't get pulled down off YouTube, right? They have fissionable material, right? Something that can sustain a nuclear fission reaction, usually uranium-236 or plutonium-239. They've got the fissionable material itself. They've got a source of neutrons to get the reaction to start, right, by neutron bombardment. And they have an explosive device. But we're not thinking like TNT to initiate an explosion, because that's like a gas explosion. The whole purpose of the explosive device inside an atomic bomb is to quickly compress everything into a small volume so that we can go supercritical. Okay? Because small pieces, if we're separated out, have a large surface area, which means that a lot of our neutrons can just escape and we don't get a chain reaction. But when that explosive goes off and it brings everything together quickly into a small volume, that forces us into a supercritical mass. Then our neutrons aren't escaping, right? They're starting other reactions. We quickly go to a chain reaction and get the explosion. Right? And here's 2 basic schematics, right, for little boy and fat man, and you see the effects that those can have. So what about the more peaceful application, right, in nuclear reactors? The nuclear reactors that we have, right, on Earth today are fission reactors, which work by controlling a nuclear reaction within a reactor. Okay? In order to control that, that means we have to have control of the material and the neutrons being produced so that we never go critical or supercritical. So what parts do we need to have, right? A nuclear fuel, which is again our fissionable material. We have to have a nuclear moderator to slow down our neutrons or capture them if there are too many. We have a coolant, something that carries the heat that's produced to a boiler. We have the control rods to absorb neutrons, and then a shield and containment system in case things go bad. And maybe you've heard of, right, where things go bad. Here's an example of a basic schematic of the Diablo Canyon nuclear power plant out in California, showing where all those pieces are. We have the coolant. I didn't continue to elaborate on that, right? Coolant carries heat to a boiler, And then that boiler is what produces the energy from the plant, right? Just like a boiler that would be fired by coal, just a different heat source here. And there's an example of a reaction core. But the containment system is key, okay? Because Chernobyl, for example, you've heard of the sarcophagus that's up there now, okay? That didn't exist back when Chernobyl had its meltdown. So what kind of containment systems do we have to have? Well, the reactor vessel itself, right, is thick steel. That absorbs most of the radiation. Okay, but then there's a whole bunch of other redundancies as well. Okay, the main shield is really thick, right? Several feet thick, high density concrete. That's going to take care of most of your radiation. But if not, you also have personnel shields to protect from gamma rays and X-rays. And if there's a meltdown, you should also have a cement dome over these things, which is the thing you see from the outside. But there's other measures that are taken on the inside as well. I alluded to just a second ago when things go wrong, right? You had 3 Mile Island, for example, in the US, right? That, though, in the takeaway I hope you get was my point earlier, right? 2.5 million times more effective than coal. Nuclear energy is the future of clean energy. Everything that's gone wrong, right, has been a result of catastrophic circumstances. It's not the fault of the nuclear chemistry itself. 3 Mile Island, right, not too far from Western New York, was a cooling system failure. Okay? And there was an explosion at 3 Mile Island. It's still classified as a nuclear disaster, but that was just venting radioactive noble gases, which was done on purpose because there was also a high concentration of hydrogen, meaning it was prone for an explosion. And venting radioactive noble gases, well, that's not so bad because noble gases don't react. Okay? Be a heck of a lot worse to vent radioactive things like carbon or oxygen. Okay? Chernobyl, right? That's the most famous one. If you have time on your hands, there's an HBO miniseries showing what happened in Chernobyl. But effectively, what was happening there was it was a late night safety test. Okay? They were simulating power failure in a station blackout. So all the emergency safety and power regulating systems were turned off. Okay? There were a couple other things that went on, including some human error that was in there, but eventually it led to a flash steam explosion and then a graphite fire. Okay? So that's obviously the worst of everything that's happened. More recently, you had Fukushima as well. Okay? Fukushima had better regulations than what happened on at Chernobyl, but nobody could have predicted the magnitude of the earthquake and then the tsunami that hit Japan. And the problem was, right, even when the earthquake was detected, the station got all the generators online, even lost the power, no big deal, everything was okay, right? But then the tsunami and the flooding came, that killed the generators and led to a hydrogen explosion at Fukushima. Okay, so unprecedented natural disasters, ridiculous safety flaw, right, in covering up by the Soviet Union and Chernobyl, generator failure. It's not the nuclear chemistry. Right? The just risk is when things go wrong, they go terribly wrong, but the chemistry is solid and the energy produced, right, sky's the limit. So how about fusion? The flip side. We've spent a lot of time talking about fission. How about fusion? Okay, fission was things breaking apart. Fusion is things coming together. Okay, converting very light nuclei into heavier nuclei. And when that happens, we have mass that gets converted to energy. We talked about that in the first video. We see fusion happen in the sun. And we see 4 hydrogens coming together to form an alpha particle or a helium nuclei. Now, fusion reactors are possible in theory, right? A fusion reactor would be a nuclear reactor in which fusion reactions are controlled. And that would give you even more energy than fission. But it's currently an area of research because the problem is for fusion to occur, it requires temperatures, right, greater than 15 million Kelvin, which is fine in the middle of the sun or in plasma and stars, but we can't get that on Earth, okay? Because to achieve that temperature on Earth, all of our molecules just dissociate into atoms, and those atoms ionize into plasma. Again, fine in a star, can't do it on Earth, right? But that has a huge possible application. There's lots of research into doing it, right, using things like magnetic fields and laser beams, but it produces even more energy than fission does, and it's cleaner energy. Okay? So that, right, if fusion reactions can be developed in our lifetime, that's pretty much an instant Nobel Prize if you're looking for inspiration to go into research. There's two other sections in chapter 21 for uses of radioactivity. Okay, 21.5 and 21.6, which talks about radioisotopes in biology and biological effects. Okay, those won't be explicitly tested in this course, but if you're interested in that, you can read over with time permits. And that concludes the videos for chapter 21.